everybody. So yeah, as Ray mentioned, I'm Srinath Vadlamani. So before I get started, who in this room has used DDT or MAP or another Alinea product? Okay. Wow. Okay. Cool. So now you've heard the word Alinea, the title Alinea with the product, and you see a lowercase rebranding of the word ARM in the bottom right-hand corner. In December of last year, ARM acquired Alinea, so now we're actually officially part of ARM, okay? So I may change back and forth between those two titles, and if I do have the word ARM in any sentence, I haven't figured out how to actually put it in so that you know it's the company and not an appendage, because they actually rebranded it as all lowercase, and there's splashy videos on the web about it and all kinds of stuff. So if you get bored, you can Google ARM rebranding and watch that. So I'm going to talk about debugging, profiling, HPC applications. Going to keep it kind of high level because we all know in this room that to really know how to use a tool, you got to use the tools, right? You can't just sit there and look at a bunch of pictures on a screen and then start salivating that you want to use the tool. You got to use it. So we'll start off with some techniques, some ideas about debugging and when it comes to profiling, what we appreciate and what has worked for us. And then I'll go through a couple of examples of the tools in play corresponding to those different techniques. I put up this website at the bottom right now. If you update your PDF from the website, it'll have these new slides. You can grab the trials and actually install them on your machine. For those that are running Macs, not Linux boxes or Windows, a VM machine is where you want to actually do a lot of your work. Hopefully people are starting to do that on their laptops and their HPC endeavors. All right, a motivation for the whole talk is a recognition that everything's finite, right? The machines are finite in terms of the resources, the amount of time you have on them. The amount of time you have is finite. People got to submit thesis or dissertations, you have projects, you got to write papers, all this in a short amount of time. So you want tools that work well, that are efficient, they're not hard to use, okay? And you also want to employ your smart ideas to do a debugging exercise or do a performance investigation. And it's nice to have tools that allow you to do that and don't require an entire new PhD to learn how to use. So jump into kind of the demonstration, proof in the pudding type of idea. We have real world examples. The first one on the left is a really small image of MAP. So MAP is a profiler, the Alinea MAP. It's part of the Forge package. DDT and MAP comprise Forge. And the reason of that is because it's part of a workflow cycle when you do software development. MAP is a profiler, a high-level sampler, okay? That kind of gives you a trace of operations. What we're really interested in here is time for instructions. And we categorize them with respect to CPU use or I/O use or memory use, okay? This example right here was at a bioinformatics problem that received a lot of speed up, and this was done in the cloud on EC2. We have an example of MAP itself as applied to a deep learning exercise that on the KNLs that got considerable speed up. And lastly, we have a fluid dynamics, actually a blood flow problem that when they were trying to scale out to 50,000 cores on Archer, they kept on crashing. And DDT, which is the right image, the last image actually shows the reason why it was crashing and allowed for a debugging exercise that successfully allowed for a full scaling on on a platform. Rarely done, but that achieved it. So I'm going to jump right into what people hopefully, if you want to argue against the slide, please do. I argued with someone who gave it to me once, and I am still not completely convinced this is the only cycle that goes along with debugging, but I think it's reasonable. So you run your code, right? It crashes. You come up with an idea as to why it crashed. You turn around, you put a bunch of print statements in it. You recompile it, you run it, and it crashes again. And you keep on going through the cycle, and hopefully one day you exit, right? Well, we all know the role of a debugger is to replace this last little orange square, okay? Now, when it comes to optimization, you did a debugging exercise, now you wanted to make the code run faster. You made it greater, now you want to run faster. So you insert timers, you run the code, you look at the results from the timers, you change the code. Because you changed the code, you may have to insert new timers, and you keep on going through this cycle to try to make it run faster and faster until you reach this roof line. These are HPC applications, right? Are you really going to hit roof lines? No, but you want to just try your best to get as much performance out as possible, and that investigation, that understanding is itself another big exercise. Well, when it comes to the tools such as MAP, or a number of non-invasive tools, you pull that instrumentation portion out of your workflow cycle, but still this process happens. So these aren't foreign concepts to anybody in the room, right? Everybody's familiar with this cycle, and we're probably all living in it right now. Half the people in the room are probably doing one of these cycles right now because they have a dissertation due in like 2 hours or something, right? So I'm going to go to the notion of debugging. And this statement that came from somebody, a famous performance expert. No, I mean, the statement makes sense. It's pretty simple. No one cares how quickly you computed the wrong answer, right? So you want to use debugging not only to fix crashes, but also to understand possibly why you're getting the wrong answer with your code. So we'll move on to some kinds of bugs. Has anybody seen this small zoology of bug terms? I was shown this a couple months ago, and I was like, that's great. Good job. Thank you. That's really funny stuff.
That's the Lacombe taxonomy.
No, actually, it precedes Lacombe by months or some months, years. It lives in a 2004 web collection of computing terms that I saw. I actually started to drill down. I didn't believe. So David Lacombe is the CEO, or was the CEO of Linea, now director of HPC tools at ARM. And he gave me this slide and said, hey, check out these terms. They're kind of funny, right? The Bohr bug, just to kind of go through it before I pick it apart. The Bohr bug is the notion that you have a dependable, reproducible, steady bug. It's your favorite type of bug you will ever come across, right? Then you have the Heisenbug. It was there, you banged your head against the computer, you went to your thesis advisor and said, there's a bug in the code, and it's gone. The code, it runs, and you're like, And then you have the Mandelbug, which is so hard to even explain that it's just the result of some chaotic process. And that's what you actually say. It's somewhere in a meeting, oh, it's stochastic, I don't know what's going on. And then the best bug in the world, the Schoenberg. The notion that once you actually start reading the code, you realize that the code should have never worked in the first place. And your advisor or the person that's in charge of your job right there turns around and says, the code doesn't work, it's broken, fix it. So that's the Schoenberg. You have to fix it before the bug goes away. And these all persist in the livelihood of anybody here that's working with software and is going to deal with bugs. And being familiar with them is not really important. Just know that everybody else is going through the same pains on these different levels. When we actually get to debugging itself, you want to go through the process of trying to transform a broken program into a working program, right? So the methodology that I adhere to is I got to track the problem. hopefully people here have some methodology of tracking their problems. You can actually use ticketing systems like Jira or something of the sort to actually track your software development. I mean, these are personal thesis projects, right? It's never going to hit the limelight. There's no reason for it. If you can somehow record your process, document a bug existed, you will revisit that issue again. It will pop up again during your work. So track it in some fashion. Making the bug itself reproducible is important. It also proves to yourself that it's not a race condition, which is like one of the worst things in the world to try to chase down. But having a reproducer or having the bug itself be reproducible is very handy. It keeps you sane, which is important in this practice. You've all accepted a challenge of being HPC people, so sanity is also one of those finite resources that I didn't put on the list. Then, if you can automate the testing of the process, that will be very helpful. This is an evolving process. Every time you go through this cycle, you're going to actually refine it, and then down the road, you're going to be able to bring on people to help you, and you can give them this process, and everybody will be able to communicate well. The next step of actually having the tracking, and then you have a reproducer, and you have a way of automating the process, is you want to find the origin of the actual bug, because you experience the symptom of the bug. You never really are given the origin of the bug, right? The variable got touched somewhere way earlier in your program, but you're seeing the cascade effects further down the program. You want to be able to find the origins of the bug. Not always easy, but that's how you fix the bug. And this notion of focusing on what the origin is and not what the symptom is kind of important. I always forget that notion, and I just get caught up in the symptom of the bug. It's like, I'm seeing the seg fault here. What is that really trying to tell me? No. You got to go back and see what kind of poor coding I did to actually cause the thing. Then this notion of isolating it. Okay, this isolating the origin problem usually results in creating a reproducer that is a much smaller set of lines of code than your actual HPC application. Who here has submitted a bug report to a compiler team? Like that, the back row has, right? It's the back row. So, you've accepted the challenge to be HPC people. You're going to give bug reports to compiler teams, okay? And I'm serious. You're going to send bug reports somewhere through your dissertation experience or through your work to Intel, to Cray, to PGI, at one day probably even ARM. And you're going to have to produce a reproducer, which is a smaller code, a very simple code that exhibits the same symptoms as your big application. This is your chance to actually learn how to start doing that, how to trim down code, how to comment it out without changing its behavior. That's part of the process. And the earlier you accept that as part of your debugging process, the easier things will be. The last step, of course, is to check to verify that your bug actually has been squashed, and having some kind of testing framework for that. You've just established a reproducer code that now you can actually put back into your application. You can test against real results. Having a test case, which sounds very similar to a unit test type of concept, is good to have. You can then put it into a regression testing system, put it into a nightly regression testing system, and that bug will never arise again, hopefully. So, suggested reading. I actually started reading Why Programs Fail. It's okay, but some people really, really enjoy that book. The really, really big reading that everybody's doing right now, because they're looking up terms and looking up these bugs, zoology stuff, is Stack Overflow. All right? Who here has not used Stack Overflow? All right. We're all part of you're all in the cult now. Right? You can all wear those special T-shirts. That's come along with Stack Overflow. Okay, techniques that go along with debugging. And these seem to be segmented or compartmentalized. I'll go through them. So this notion of automation, test cases, and bisection via version control. Bisection via version control, who here has that as their go-to debugging method? Pass the buck to someone else type of method, right? Okay, so, I mean, it works when it does, right? And then you have the observation methodology, where you put in a bunch of print statements and you find out where things look kind of wonky. Or you don't put in print statements and you use a debugger to scope your values. Then you have the inspiration, the talking to the duck type of methodology. Who's heard of that terminology?
I have the duck, actually.
You have the duck. Yes. So my children have the duck too. But they don't talk to it about code. They do other things with it. So talking to the duck idea is where you sit down with somebody who's a non-expert when you're experiencing the bug, and you start walking through the code. You talk through the code line by line. And as you do it and you think about how it's supposed to work, you may actually realize what is causing the bug, okay? And the last notion of, they call magic, I would write like maybe wizardry, no. It's another way of looking at the code by using other tools, say a static analysis tool like CCP check or FT check, and then do memory debugging, where you're actually looking through memory leaks, dangling pointers, things like that. It seems like wizardry when you try to explain it to someone else that you did this activity. All of these are going to be in your toolkit, in your tool or your tool belt when it comes to debugging. You're going to use every one of these methods, all right? And it's all of them are they're all equally useful. So don't shoot down one versus another just because you think it's lame to try to explain the code to someone. It's quite useful and it'll help. There has been an ideology of when you go after bug issues, you're trying to go through an investigation. So you're trying to answer who, where, how, why. And it's kind of a nice idea, right? You're kind of like a reporter and you're trying to find out why it's happening before you can actually fix the issue. Because if you don't have a clear understanding, you're actually just you're fixing a symptom and not fixing the problem. So with the who, you want to understand what's actually bombing out on you. So stack frames, a notion as to what the stack looks like is helpful in that case. When you have when you want to know where it happened in the code, being able to leap to the source code, the line of the source code where the offending portion of the stack is happening is useful. How did it happen? Well, you want to be able to actually scope the line of the code and see what's going on within the code itself. And then why did it happen? I want to look at the variables. I want to actually look at the notion of what the variables may look like across a spread of 20,000 cores. That's helpful too. And in the Alinea world, in DDT, the way we look at that is called a spark line. And so the images on the right, or the image on the right is a stack trace in terms of a parallel stack trace. Yeah, hopefully you guys see, what is that? 150,000 and 220 core MPI ranks on the right-hand side. Do you see that? Okay, that's the number on the top left-hand side. As the branches expand, you can see what the different MPI ranks, what their state in the stack with respect to the stack trace is. That's offered up in DDT. In the bottom right-hand side, you can actually look at variables themselves and see what is called a spark line, which is this bottom, or this little square right here. Trying to give you a depiction, some kind of like an overview as to what the values, the variability of the values across your MPI rank set. That's helpful too. So we have this list of favorite features with DDT. So there's the parallel stack view, as I explained, automated data comparisons. That's the notion of spark lines, being able to look at different MPI ranks and what their values may look like. Parallel array searching. That is an incredible feature. That's not an advanced feature in DDT, but definitely something to exercise, go through examples, and learn how to do. If you can do this whole suite of things, then you're off and running with DDT. So the notion of standard debugger is that you can step through code, you can play, you can set breakpoints. In DDT, you can set watch points and trace points, so you can watch when values actually change throughout the execution of the code. Again, hands-on stuff, going through the manual, you'll learn how to do that. And a pretty cool feature is this notion of offline debugging. So you're having trouble actually getting connections, you sent off something to queue, and you really want to hopefully get some results in the middle of the night, but you're off doing something else. It's possible to get a large amount of the debugging data dumped to a file of which you can access later and use the tools with. Again, all of this happens in parallel and happens to scale, all right? So when we go to performance, because we debugged the code and now we're actually going to try to eke out as much performance as possible, 6 steps that work. You can insert a number of steps in between, around the sides if you'd like to. So you always want to have a realistic test case. Realistic in a lot of people's arena is something that probably has the similar memory footprint as to your real production application, okay? I think everybody here has probably seen a few talks on what memory pressure and how it impacts your performance of an operation of an application. That's an important thing to have when it's a realistic test case. Then you go through the profiling of your code. There's multiple tools out there. We offer up MAP, profiling your code in a very introspective, very detailed way. You can use Tau, the V2 when it's on the Intel ecosystem. This notion of look for the significant. You have to discern what is important when it comes to the data that you receive from your tools, right? You need to either decide, is flops going to be the most important thing you're worried about? Is time to the end of execution the most important thing? I think so. Things of that nature. And of course, you need to distinguish what the problem is that you're trying to, what experiment are you trying to solve right here or explain, or what kind of hypothesis you're trying to explain with your experiment? Why is the thing so slow in this particular region of the code? Then you apply your very smart brain to solve the problem, which is you come up with some really good ideas, bounce them around. Once you've achieved your optimization, you need to bottle it. This is somebody else's term. You can imagine they're British, and they say, bottle it. So bottling is this notion of locking in the performance, okay? So throughout, I think I've had a couple of slides where I've kind of declared you need to document your process, okay? You need to be documenting what's going on, particularly with the debugging and your performance exercises. One, it's going to convince you that you know what you're doing. Two, you're going to be able to show to someone else and convince them that you actually achieved the performance for the reasons that you explain in your documentation. All right, so you lock in your performance, nightly regression tests. That's very helpful to have this type of performance, this performance exercise, this test experiment as part of your nightly regression test. And then if you have bug fixes, you want to bottle them, right? That's the notion of documenting what they are. You created test cases to expose and then fix the bug, put them in your regression test. Lastly, regression tests do help you from regressing. All right, the last thing you want to do while your time is finite is to keep going back to the same problem over and over again. Here is a fun slide. Some people have probably seen brochures from Alinea. Similar things appear in people's books that may be in this room. This notion of racing and optimization. simple ideas. Analyze before you optimize. Know what your code looks like and how it performs today before you go through an optimization exercise. Get familiar with your code. Know what your I/O looks like. Know what your MPI usage looks like today before you try tackling making it work better in different regions of the code. So we have I/O. Workload balance is an important feature to look at. Once you're confident that you have some good workload balance, and moving on to the communication patterns, intranode or between nodes, your use of multiple cores is an interesting aspect. Threading, especially the fact that we're getting to more and more cores per chip, is making this a lot of effort will be spent there when you optimize your codes. And then lastly, when it comes to vectorization, there's a number of books on how to vectorize codes. And I would think that everybody in this room probably knows the first tool to use when it comes to vectorization. It's the compilers, right? They spit out pretty good information as to why things aren't vectorized. Always use that information. So here is a very it's a reasonably busy slide on this notion of how the tools fit together. You have a bunch of demands on the left. You have things that you actually do as a programmer on the right-hand side, and you're trying to always make things better and faster. The tools themselves, we kind of insert in between. People want things to go faster. You want to make sure that you don't regress. You have a system of how you're going to go through your software development. We have this notion of we have this tool, performance reports. That I will show in a second is a high-level view of the performance of your code today with no recompilation whatsoever. And then to get more detailed information, you go with map to actually increase the optimization. You go for it. You break the code. You use DDT. You go back to map, or you use map or use DDT because you didn't break the code, but you really want to know why a particular region of the code is behaving the way it is. It's a debugger. It gives you a lot of information as to the operation of the code. This is a fun slide. I think some people have probably seen this one before. It's this notion of, as HPC users and programmers, it's important for you to transfer the notion of performance to the actual scientific community, so that they can appreciate it, because a lot of them don't even know that they're suffering from, what's a good term? Suffering from the fact that they were leaving so much performance on the table. They think that they have, they're getting the answers, they're really happy with it, they keep on expanding the code and making it solve more difficult problems, but they have no idea they're only using 3% of the actual, or 10% of the actual chip. And so it's kind of your job to actually explain to them that performance is important, and they need to appreciate that. To help you get across that message, we have performance reports. So one section of a performance report is just giving simple CPU information. And these 4 items are some simplistic metrics that go along with CPU activity. I'm sure everybody's wondering, how the heck do you get those numbers? Where are you getting these numbers from? That's not the point. The point is that we're trying to give you a way of displaying information quickly and easily to people that need to appreciate that information to help you accomplish your goal. Okay? There's some nice information that goes along here. You have this notion of single core code. So in this case, it is a single core application. You're using 100% of the time is spent on the single core. And then it goes through simple listing of different metrics. Scalar, you can imagine what that is, right? Scalar flops, and then you have vector instructions that are being measured. And then how much time of the entire application is spent in just doing memory accesses. So that's your whole litany of L1s and L2s and so forth and so on. Yeah, we'll bypass that. We'll go into this notion of, again, if you try to explain to people that are not really interested in understanding how a chip works, just so that you can convince them that performance is important, then you're going to start talking about out-of-order execution, right? Then you're going to start talking about pipelining the code, and you're going to try to explain the complexity of switching contexts and so forth, and you know all the nuances that go along with trying to actually get to the point of executing and then retiring an instruction. When at the end of the day, all they worry about is, did my code execute in a certain amount of time? Did my instructions execute in a certain amount of time? And that's what we try to display here. And simplistically, a simplistic form, hey, you know, no time was spent in vector instructions. All right? So go to your compiler, put in the special flag, see what it suggests as to why it didn't vectorize your favorite loops. And I put down here, yeah, your compiler device is your friend. Use it. It's there. So this right here is actually what the left-hand side image is what performance reports looks like. You run performance reports on your code, it produces an HTML file, and you mail that off to eventually your program manager. This is what my code looks like. And then the next week you mail it again. This is me optimizing my code. That's pretty cool. On the right-hand side, we have a lot more metrics, a little more detail as to what those metrics are. Here we do break it up, CPU, I/O activity, memory activity, MPI activity. And then if your application is threaded activity will be displayed. You know, that's in regions spent in whatever threading library you're using. If you want to look at energy as a collection of metrics, that's available. The newest versions of report actually has better accelerator support. So if you're kicking off kernels, you can see how much time your overall application is spent in those kernels. Again, high-level report. So then you go through this notion of what an application development workflow looks like. You profile, you optimize, you execute, you break the code, you debug, you do some coding, hopefully it works, and you profile, again, the resultant so that you keep on making the code run better and faster. Here is what we offer as a combo for Forge as DDT and map to help you with the process of the workflow I just showed. The Forge tool, a great feature. I love the fact that we're working on remote machines. We're all working on these iron horses out there. And we love forwarding so much that we love sitting at our desk and just watching that window pop up in 30 seconds after hitting a return, right? No, you want to be able to do a remote client scenario. So Forge is available as a remote client scenario. You can download the client and use it for free and connect to any machine that has DDT or map running. There's some caveats with versions, but we can iron that out. The client itself natively runs on Linux, OS X, and Windows. It handles multi-hop SSHs. Who here has, that's their common workflow. You go through 3 different machines, right? And you pull out 4 different crypto cards along the way. It allows you to do that. It blew me away. It actually works. And then hopefully your remote system has a server license scenario so that you don't have to worry about managing any licenses. Map, in a nutshell, it's a profiler. It produces small data files. We don't embed the source code, though you can actually see source code here. Necessary, there's caveats as to how to get that source code to appear, but the map file itself is usually in the megs or less. Overall goal of map, its purpose is to give you a high-level profile of your code, okay, and to give you some kind of notion of a trace with very low overhead. So we're always trying to live within less than 5% overhead, be it time slowdown, be it memory usage, whatever it may be. We try to live within that. And that constrains how much information we can actually give in the tool. There's no instrumentation whatsoever to get this tool to work on most platforms. And no instrumentation whatsoever, there's no recompilation that's necessary to get it to work on most platforms. So above all, this is the notion of what you want to do with map. And it gives you the high level appreciation of how your code's behaving now. You do your optimization, you can see it again. Here is an example of a 512 process where you can see the memory usage of the code itself during the duration of the code, how much time was spent in MBI calls at what particular duration in the code, the floating point usage on the CPU itself, and then you try to solve, okay, where's the bottleneck of this code? Well, right down here, it shows that 34% of your application is being spent in that function right there. And this was just running the code, I mean, just running map on your code. And simplistically, that sucker, why isn't that popping up? There we go. It says, hey, fix your code. Stop reading from the file or dumping to a file so often. That's all it's that, I mean, it's simply, you see that this file write is happening in a periodic fashion, and it's questionable if you need to be doing that. So it's kind of hard to tell people, hey, stop writing restart files so often. They don't like hearing that, but you can show them the effect of it. That's kind of cool. So there is this notion of being able to drill down into actual CPU usage. Again, we are the ones that describe what those different values are. I mean, we write the formula that we aggregate together to say what the collection of percentage of CPU floating point vector is. And if you want to know what the details are, please ask me. I can always point you to some of the developers because they've come up with some really interesting ways to aggregate that information. So this particular application, you have, you know, it's accessing memory in a particular way. You see a lot of floating point usage, but all the vector instructions are not being retired whatsoever. And they probably never even issued. So what is the problem there? Well, most people will just punt, or you can go back to using your debugger. A debugger will help you understand what's going on. Now, if you did configuration of your map trial using, using the front end, using the remote client scenario, you can now switch over to DDT immediately and actually run your application under DDT now, because all the configuration, all your batch scripts, everything's already been set up. So it allows you to integrate that really easily into your workflow. So here we go. There has been 50,000 cores was the largest profiling that's been done, and that was very successful. We have cases of debugging happening at thousands of cores. It's deployed on a number of machines. Unfortunately, there's not a European machines here, but around the world, there's machines that are using the Forge suite. And we want to have the tools be of low overhead, both for your brain and also execution on the machine. I'll revisit these 5 great things to try with the Linea DDT. So scalable print alternative was used looking at the spark lines themselves. You want to be able to stop on a variable change. You want to be able to do trace points, breakpoints, watch points. Static analysis, since we do use CPP test and F-test. So statical analysis is available. Then you can scope the bounds. You can see if you're actually writing out of bounds for a particular array. And stale memory allocation, this is all available through memory debugging. With map, you can do some cool things. Like you can actually look at memory performance across the application, which you're going to find be most problems you're going to experience. You can fix MPI imbalances, bottlenecks. These are exercises that when you start playing with map, try to do. It would be good to actually collect a number of examples. We have a few to highlight these. Make sure OpenMP regions make sense. That's an interesting one. To let you know, OpenACC is supported with map and DDT. So that's in case everybody or anybody's worried, and CUDA kernels. Improve memory access and restructure for vectorization. Here I got a couple of little tidbits on how to get things started on Theta. I think we got most things resolved. Map is being kind of wonky on there, but we'll deal with that during the hands-on. And the hands-on session, you can either grab trials yourself, or I can point you to some examples. You can try these tools on, or you can just start off running with your application of interest. If you have access to a machine where your application is and these tools are installed, or we can install trials of these tools on your machine. All right, thanks for your attention, guys. So, questions? Yeah?
So you mentioned the overhead on map. What's the overhead for those reports?
All right, so the reports use map. Yeah. Any other questions? Yeah, go ahead.
In the multi-threaded application, usually if you stop the program, so the threads continue, and the code does not behave the same when you debug and when you don't debug. I mean, when you break a breakpoint, so one thread stops and the other one continue. How does it behave in DDT?
Okay, so you're asking the question is if I have a failure happening with one particular thread and other threads keep executing, that is the behavior of my code?
And then if everything works fine, when you put a breakpoint, let's say with a simple debugger, not especially for multi-threaded, but you have a debugger, you put a breakpoint.
Yeah.
So one thread gets there, and the other thread continue.
Okay.
So how do you have
So,
such complexity here? Or no?
yes, so DT offers the capability. It actually queries you. Do you want the other threads to, okay, so once a process hits a breakpoint, application pauses, and it queries, do you want all the other threads to continue until they hit that breakpoint? Or do you want to pause right here and start looking as to where every thread is at that state? Does that answer your question?